Good afternoon, class. How are you guys doing? Everybody's fine on this cold winter day. Yeah, but we're going to be covering some really cool material. Our target today is gradient descent, the engine of the AI revolution. We'll start by warming up with a simpler problem that will get us thinking iteratively, and then we'll move into gradient descent. So, the mathematical tool we're using is called partial derivatives. These are just ordinary derivatives done one variable at a time. So if f depends upon several variables, you hold all of them but one constant, vary the other, and that's how you calculate the partial derivative with respect to, say, the ith one. Now, because we know linear algebra, we can work with functions that are vector valued, not just variables that are vector valued. And then it's natural to package up all of the partial derivatives into a matrix called the Jacobian matrix. So the first column of the Jacobian is the function's partial derivative with respect to x1. The second column is the partial derivatives with respect to x2. And then finally, the nth column is all the partial derivatives with respect to xn. When you take and write it out, it's kind of frightening, but it's straightforward to figure out what goes in which entry because, for example, here, the second component of f with respect to x2 is the 2, entry of the matrix. The second row, first column is second row of the function, and then the first variable x1, etc. And we only compute these things by hand for toy problems. We use symbolics.jacobian or forward diff.jacobian to compute the Jacobian matrix. Use the symbolics if you want the Jacobian as a function of x that you can then do something else with. And forward, you use forward diff when you want the Jacobian evaluated at a point, and that's what it does, a point, say, x0. The utility that we're going to be exploiting today is the linear approximation of a vector-valued nonlinear function about a given point x0. And just like in the scalar case where it was y of x equals b plus little a times x minus x0, here it's the same thing. The b is the function evaluated at the point of interest x0, and the little a is replaced by a matrix, and that is the Jacobian matrix. And so this tells us how f varies locally near x0 and turns this nonlinear function into a linear approximation. And so today we're going to do a ton of engineering applications of vector derivatives. And as our warm-up problem, I would like us to compute the Jacobian of this function I have here. So the function depends on two variables, x1 and x2, and the function has two rows. So the Jacobian matrix is going to be 2 by 2. Okay, so the first entry is df1 with respect to x1. If you continue in this row, it's this function's partial derivative with respect to x2, and then second row partial respect to x1, second row partial respect to x2. Give it a go. On your mark, get set, finish line. Got it right here? I can see you're doing the calculations right here. That's where I'm doing them. Okay, let's see if we can get the first row. That's the hardest one. So differentiating the exponential, we have to repeat the exponential. And then we need to multiply that by the derivative of this function with respect to x1. When we differentiate with respect to x1, x2 is a constant, so sine of x2 is constant. And so that's what we get here. Sine of x2. So that's the 1, 1 entry. The 1, 2 entry, we're still differentiating the exponential. And then the chain rule says compute the derivative of this function with respect to x2, so then x1 is a constant and x2 is a variable. And so we have x1 is the constant, derivative of sine is cosine, and if that had been x2 squared, then we'd have to do the chain rule again, but we don't. Look pretty close to what you were getting? Yeah? And then the next one is a polynomial, so that's much easier. Respect to x1, power rule gives us 6x1, and then x2 is a constant. Okay? And then when we differentiate with respect to x2, this goes away because it's a constant, and we only have x1 multiplying it. So that's the Jacobian, and we almost never do anything more complicated than that by hand, and it's 2 by 2 because there are two unknowns, x1 and x2, and the function takes values in R2. So the number of rows of the function is the number of rows of the Jacobian, and then the number of variables is the number of columns. So we have the rows and we have the columns. Questions on that? Solid? We can do Jacobians. We don't like to do them by hand, but we can for simple functions. Cool. Okay, so here, this was covered pretty well in Rob 101. The linear case is reviewed here in case you need it. But what we're going to do now is work on the nonlinear version of root finding. And once again, so this was a topic that was treated in chapter 11 in Rob 101. So we have a function. When we're doing ax equals b, if we want there to exist a unique solution, we typically like a to be square, and then all of its columns linearly independent, which is the same as the determinant being non-zero. So the equivalent of a square matrix is a function that has the same number of dependencies and variables as it has rows in the function. So it's square in the sense it maps Rn into Rn, which is what a square matrix does. Now we're typically letting x1, x2, x3, etc. be the components of x, but when we're doing iterates, it's very convenient to denote them by k, where k is the kth iterate, for example, so we are going to be abusing notation, and you'll have to use context to decide, are we talking about the kth component or the kth iterate of the vector? Okay, so it is an abuse of notation. So in this way, when it's the kth iterate or the kth index in our for loop, it will have a first component, a second component, and an nth component. So x is an n vector. X is an n vector. What we're trying to find is a sequence of n vectors. Go away. Go away. Where'd you come from? I don't even know. Oh, I must have touched something over here. I got it. One more to go away. We're seeking a sequence of n vectors, so we'll start with some initial guess, could be poor. And we want a sequence of improving guesses such that in the limit, f of the limit is actually 0. So that means that x star, which would be the limit of us iterating until our tolerance becomes small enough, we want that to be a root of the function, which means that the function evaluated at that is 0. So the term root comes from like the quadratic equation, and you calculate the roots of the quadratic polynomial, okay? So that's where the term comes from. It's just the zeros of the function. So it's vectors that zero the function. Does this ring any bells from Rob 101? Or has it been too long ago for some of you? Your organic circuits are still firing on that? Good, okay, so. So the question we want to confront is, if we have a current guess, how do we find the next guess that gets us closer to being a root? And the fundamental idea that we're going to exploit in gradient descent is that we replace the function by its linear approximation. So then the function now looks like, when it's evaluated at our current guess, this is just an n vector, a constant. This is an n by n matrix of constants. And then this is x minus xk. So that's just the standard linearization. And what we want to do is choose the next value, the next iterate, such that f of xk plus 1 is approximately 0. And so the idea is, well, we don't know how to do that if we work with only the nonlinear function. But if we're working with a linear equation, and this is b plus a times x, okay, so it's a linear equation, we can just set b plus a times x equal to 0, and then solve for x. And so that's what we do. We plug in xk plus 1 for x. We'll call that delta x. And we're going to solve for delta x such that it is a root of the linearized equation. When is that linear equation going to have a unique solution? So this, if this is n by n, we need the determinant of this matrix to be non-zero. Same thing as the columns being linearly independent. And so that gives us the algorithm. Here, if we bring f to the other side, that gives us a minus f. And then we want to multiply by the inverse of this matrix. But hopefully it's still part of Rob 101 lore that real roboticists don't hang out with people who compute matrix inverses, okay? So what we want to do is use something much more robust than computing the full inverse of the matrix. And so we're going to use a solver like LU or QR, and the backslash command in Julia, it will look at this matrix and then decide whether it's more efficient to use LU factorization to solve for delta X or to use QR factorization to do it. So you don't have to worry about it. It makes a good choice. And then you get your update, delta XK, because XK plus 1 is delta XK plus, oh, come on. Where did you go? There we go. Okay, it inserted a page, but we'll live with that. There's the algorithm, and I'll remove that later. And then if you don't fully trust the linear approximation, what you do is you put in a step size, S, that's positive. And so 0.1, 0.2, and then you only update partly in the direction defined by delta X. And then you iterate that, and it's called the damped Newton-Raphson method. Okay, does that get some neurons firing? We've seen that before. We do iterative approaches to solving nonlinear problems. Cool. Questions? Ready for a demo? Excited for a demo? Maybe excited's a big word. Excellent. Okay, so these are demos available in Chapter 6, Part 2, Class Demos. And that's Lagrangian mechanics, which we're not doing today. Awesome. Okay, and that was the path length problem that we did on Monday. Oh, come on. Be nice. Scroll up. Bingo. Okay, so root finding in Julia, we're going to use a package called nonlinear solve, NL solve. And so what it's doing is everything we just outlined, okay? It'll take the function, compute its linear approximation, and make a very good choice of the step size for you. Okay? Now, the function I chose for us to have is, depends on two variables, x1 and x2. One of the functions forms a circle, and the other one forms a hyperbola, and there'll be a positive solution and a negative solution because of the x squareds, okay? And so what we're looking for are intersection points of the circle with the hyperbola. And if I had chosen my initial condition over here, it would likely converge to this point, etc. So this is the root found by nonlinear solve. So it's you give it an initial guess, you give it the name of the function that you've called it. I called it system of equations. The exclamation point just means that it's doing return in place. So you don't have to have a return statement. It's trying to be memory efficient, and an x comes in and then a function values come out, okay? So it's just using those variables to return everything. You don't have to use return in place, and the textbook shows you both formulations. And then all of this stuff is just to make the plot. So that's how hard it is. You write down your nonlinear equations, you give it the initial guess, and you call NL solve. Then the root will be result.0. It's a zero of the function. Okay, and then depending upon which initial condition, and this is just showing that it did a pretty good job. You can set the tolerance, and the default is around 10 to the minus 10, so it's pretty darn good. Here's a much bigger problem. So it's got 9 unknowns and 9 components of the function. I can't make a plot of this, okay? I'd have to go in 9-dimensional space and do intersections of 8-dimensional surfaces to find one or more points, okay? And so this is where NL-solve comes in. You make an initial guess, and it's pretty far from where the roots were. So it did a pretty good job. And the function values are, well, that one it got really small, but e to the 10 to the minus 15, minus 14, et cetera. So it does a good job, and it's much easier than you setting up Newton refs in yourself. It's also doing something called line search. And so if you have a point and a delta x, so you have a direction, instead of just moving all the way on delta x or just taking 40% of delta x with a step size, you could just put 30 points on here, evaluate the function on that, and then take the lowest value. That's called line search. So it's pretty efficient. So it has heuristics that decide when to use all of these different tricks of the trade for finding solutions, and it does it for you. We're going to need this when we do gradient descent with constraints, because we don't want to be running in the background our own system. Okay, so let me show you a robotics example where root finding is important. So I've got the video open. See, that's a robot. This is called the end effector or the gripper. The word end effector is a little bit more general. So if you have a leg, you wouldn't have a gripper on the end, you'd have a foot. And so the end effector would be the foot. Okay, so it's just a thing that's at the end of the robot link. Okay, so this is an arm. Thought we got you on full screen? Yeah, okay.
Which is arguably one of the most interesting and by far the most used concept in the world of robotics. It is also called backward kinematics, since it is the opposite of forward kinematics.
Backwards kinematics.
Let me explain what this is with the help of this fancy robot that I have right here. So this is a 3R robot. It has got 3 revolute joints.
So that's 3
Each
degrees
joint
of
has a
freedom,
motor attached to it.
3 different angles.
Each joint can rotate independently.
That's the world
and
frame.
There is an object that this robot needs to pick. So the
It draws
question is,
blocks
how
better
much
than
should
I
the
do.
motors rotate in order to bring the gripper to grab the object?
Okay. So your robot could have any number of links and joints connecting them. They don't have to be revolute, which means rotation. They could be prismatic, which means they move on a linear line, okay? And you want to pick something up. So what you are specifying is a point in 3 space. The function is, if you scan through the 3-link manipulator part on chapter 1, you're just using trigonometry to use angles and lengths to calculate the position of the end effector. The function you're trying to solve is, what are these 3 angles such that this gripper moves to here? Now, you don't want to solve it just once, because you're going to plan a path for this moving to the object, and who knows, maybe there's Max standing here, and the gripper needs to go around Max before getting to the blocks. Okay, you guys are doing crazy things like that in the Rob 550 lab, Max, okay? So you'll be solving this every 10 milliseconds, okay? So you need a fast algorithm to take the path that the gripper is going to follow and turn that into commands for the motors that are commanding these joints. So that's the root finding problem.
So this is the position that I want the gripper to be at.
Draws really well. I'm
So
jealous.
inverse kinematics is just that you are given the required end effector location and orientation, which is this one, and you have to find out what robot parameters are required in order to achieve that. So in this case, the robot parameters are the three angles, theta 1, theta 2, and theta 3. Isn't this...
Okay, so you can watch this more on your own if you want. So I'm just going to skip through. In his video, it's for people who have not had a course like this one, where the only way to solve equations is you put the position in 3 space, you write down all of the trigonometry, and you literally solve in closed form those trigonometric equations, okay? That works for really, really simple robots, but anything decently complex, it doesn't, and you need numerical techniques to do it. Okay, so if you can solve it analytically, that's amazing, and that's what he's doing in this particular case. But for what we would do, we would set up the equations just like this fellow does, but then we would seek a numerical solution. We would implement that in code on our robot. And if you take Rob 320, inverse kinematics is part of it. And once again, inverse kinematics is I've got joints of the robot location. That's what I control with the motor. I want my end effector to be in a position. This is given. I got to invert from this position to the joint angles of the robot to make the end effector get here. So that's root finding. Happy with that? You got it, why it's important, and then NL solve. Cool. Okay, so we're going to move on to optimization. I just want to show you a robotics example where optimization works. I don't know if you watched the Olympics over the summer. Come on.
Who would have thought there would be someone
Snoop
cooler
Dogg,
than
he's
Snoop
not a
Dogg
robot,
carrying
okay,
the
so-
Olympic torch. Enter Kevin Payette. The adaptive tennis star carried the torch in Paris.
He's
with the
paralyzed
assist
from the
of
waist
an
down.
Exoskeleton. Payette, who was
And this
paralyzed in an
exoskeleton
accident
is
11
providing
years
all
ago,
of the
has been
balance
assisting as a pilot
and moving
with
his
Wondercraft,
legs, okay?
Debuted the robotic walking device in 2022.
And it's being done in front of
primarily used in
thousands of
hospitals
people
for
live in
rehabilitation,
Paris and then filmed, and so
particularly
millions
strokes,
of people
although a
talk
personal
about
version
stress,
is being
okay?
developed as well. Besides tennis, Payette also
So it's a
competes
startup in Paris that is building this. They've got certification, the equivalent of the FDA in Europe, and they're seeking that now in the US. Now this is a much simpler version of a walking robot. It has 2 legs and a torso. It's roughly what that exoskeleton was, but it had also knees, it had ankles, and it had motion in 3D, not just in the plane, okay? But this is something that we could model using methods we develop in this course. Now, if you're designing a walking gait for this robot, what are the parameters that you can change? Well, there's a motor here for, call this the left leg, and there's a motor at the hip for the right leg. And so what you can control is the torque produced by those motors. A step, when a human is walking, it lasts roughly 600 to 700 milliseconds. How fast do you want to update the torque on the robot? Fast as you can, probably, okay? Because if there's a disturbance on that exoskeleton, the leg has to change its positioning quickly to prevent the person from falling, right? So let's suppose you're updating it every 10 milliseconds. On my Cassie robot, it was actually every half millisecond, okay? So then if it's, 600 milliseconds long, we're doing every 10 milliseconds, we've got 60 different torque levels to decide upon for the motion of these legs. And there's 2 legs. That's 120 decision variables for us to make for 1 step. So that's the typical size of an optimization problem. Hundreds of variables. What do you mean the GIF is not found? Oh, well. There it is. Okay. So this robot doesn't have knees, so it has to drag its feet when it's walking. Okay, so you add knees, and now you've got twice as many motors, and instead of having 120 variables, you'd have 240. Okay, then you add the ankles. Now we're up to 360. And now we let the hips go out in the plane. We've got 2 more joints. We're at 480 decision variables. Okay, so the question is, what are the things you would like to accomplish when you are designing this type of a gate for the robot? Well, the motor torques are drawing current from your battery. Is the battery going to last longer if you draw more current or less? Pretty clear, okay? So you want to minimize current in order to have longer walking times. Now, when the foot comes forward and hits the ground, do you want that impact to be harsh and jarring the robot, or do you want it to be soft and making it comfortable? So there's all these different considerations that go into what defines a good gate for a robot. And it's the same thing for picking and placing things or any other type of optimization problem. So you have to define a function that captures what you think measures the quality of a solution to a problem. So I want to design motor torques to make this thing walk. Okay, and so I'm going to say my function is the sum squared of all of the torques used, because torque is proportional to current when I have a DC motor. So I'm minimizing the draw on the battery. And then I may want to add some constraints. One way to use no current is to not move, okay? So if you just minimize current and you don't impose a constraint that I'm going to be walking at least 0.9 meters per second, kind of a standard rate for a human, okay? So that's called a constraint. I set the average velocity. So I minimize torque, sum of torque squared, subject to additional constraints. So your optimization problems are typically constrained. And then I could take the foot hitting the ground and I could put a constraint that causes no more than a certain amount of jerk in the system. Jerk is the time derivative of acceleration. So you feel it in a car sometimes. If you've been in somebody who's just learning how to drive a stick, then you get it a lot, okay. Okay, so you see where these problems come from? You have to, as the engineer, decide what is a good cost function. And here, motors and batteries, it's kind of motivated by that. In a different situation, maybe it's closeness to the target. You're trying to minimize the error, or you're trying to minimize the average error when you move the robot into 6 different locations and you accomplish it all in 35 seconds, okay, something like that. So those are the type of problems we're going to start working on now. Questions? Okay, so we're going to do gradient descent. And that's the backbone of all of the training algorithms. You've heard of backpropagation, et cetera, that are used in the large language models. So the AI revolution. So now we'll start taking notes. So we're going to have a function that depends upon several variables, but yields a scalar. So it's a scalar valued function that assesses or measures the quality. We also call it optimality. Of a solution to a design problem. Where X in Rn parameterizes potential solutions to the problem. Okay, so each X in Rn is a different solution. And I'll ask you to, think of X as the motor torques in a robot. Just one example. Okay, if I send different torque profiles, I get different motions of the legs. So I get different solutions to the walking problem. So each torque profile is a different solution. Some of them will be good. The robot actually stays upright. Others will be terrible and the robot falls. And so this function f is measuring what I think about the solution. And for us, we were using in this brief example the sum of the square of all the torques over the gate. And in theory, we would do the integral if it were functions. But if we discretize the torques, the integral becomes a Riemann sum, and then it becomes just a finite thing, okay? So f is often called a cost function. hopefully one looks like the mirror image of the other. It's almost, okay. Okay, my X star is not identically lined up, but what I'm trying to illustrate here, if I minimize this function, it's the same thing as maximizing the negative of the function. It gives me the same value. The cost has the opposite sign, but the X star that minimizes F is the same as the X star that maximizes minus F. And so minimizing F is the same as maximizing negative F. Okay, so if those two problems are the same, we only need to solve one of them. Because if you have a solver that does maximization, you just give it minus your cost function, and then it will be the same thing as solving the minimum of that problem. Okay, so you need to solve one of these. Of these versions of the problem. And most solvers choose minimization. There are a few that do maximization. They exist, okay? So what we're doing is we seek X star equals arg min, and I'll define this, of f of x subject to x in the domain of the function. And we'll keep it simple. We'll take it to be Rn. It's not going to be a sphere or anything complicated like that yet. Arg, it stands for argument. So remember, that's what this thing is called in a function. That's its argument. Arg min is the value of x that minimizes f. Now, I'm going to put the in quotes because, I don't know, just imagine my function were sine of x. It has a lot of minima. Okay? Imagine my function is e to the minus x, as we talked. It has no minima. So when I say the, it could be a set of values. And if you think about it as a set, that's great because the empty set is a set, okay? So there's no solution. So when you say the, that usually means a unique solution, and that's not always the case, okay? So x star we'll be using to denote, that's what we're trying to find, the value of x. So we want f of x star to be less than or equal to f of x for all x in Rn. So that's what it means for x star to be the arg min. Okay, there's a value and it's less than or equal to any other value of yields of value that's less than or equal to f evaluated at any other point. Now, finding the one that works for all x is very hard to do, okay? So the practical thing, and what we often do, is we settle for a local solution. And what that means is we find an x star that's less than or equal to f of x. When x is close to x star. Okay, so you put a ball of radius delta around x star, and then for all other points, the function is bigger than or equal to that. So that's a locally optimal solution. Okay, so you see what we're trying to do? You got it? Makes sense? A little bit? Tiny bit of sense? So let's see what these cost functions might look like. It fit? Yay, it fits. Okay, so in a typical calculus course like Math 115, you probably looked at minimization of functions that depended upon a scalar. Okay? So this would be a local minimum. In our picture, it's actually global, okay? But if this extends down, then it's not global, okay? This would be a local maximum, but if this extends way up, it's not global. So these points are characterized by the slope here is 0, so the derivative of the function is 0. Local max. This is called an inflection point. Local min. So the derivative being 0 is how you find those points. We'll see why that is true in the vector case as well. Here I'm showing some cost functions that are a little bit more complicated because they depend on 2 variables instead of 1. This image is literally called a saddle because it looks like a saddle, okay? It's essentially the vector version of an inflection point because you're locally minimized in one direction, but you're locally maximized in another, okay? But you still have a point where the derivatives all vanish. And then it's very easy to have cost functions if you design them, I don't even want to say poorly, but without a huge amount of physical insight into the system, you can end up with lots of local minima. And that is the case, unfortunately, with that walking example I gave you, with something so simple as adding up torques. You would think there would be a nice, beautiful global minimum, okay? There may be, but you're going to be stuck often in a lot of these local minima. So you would be trying to start here, and then we're going to do what's called gradient descent. But maybe the real true minimum is over here, and you start, and then you get stuck in one of these local solutions. So that's just life, okay? So but that's what we're trying to do, is to start here and then end up here. How do we do that? You could just discretize space and evaluate the functions and do a brute force search, but that doesn't work very often, okay? So you need to do something better than that. It's 5:20. I guess we could take a quick break. So we have our function that depends upon many values. If we are training a large language model, n is in the billions, literally, okay? We're going to write f of x using our linearization. So it's the same strategy that we followed for root finding. So if we have a value and we move a little bit away from it, how's the function change? It looks like this. And if I plug in x0 plus delta x here and I subtract off x0, all I have left is delta x. Okay, and so fact. Points where we don't move so I take f and I perturb myself away from it in all possible directions. So I'm going to have an algorithm, I'm going to be at a point, I'm going to move. I want my function to decrease, but if I'm at a point, and no matter what direction I choose, that only happens if this matrix is 0. Okay, because if it's non-zero, I can always choose a delta x such that the product is non-zero, and I can change f. Okay? So that's if and only if the Jacobian at the point is 0. And that's, let's see, that Jacobian is 1 row and n columns. So the Jacobian is a function. It's the first partial derivative, nth partial derivative. So it's 1 by n, as we said it was. And so definition x0 is a stationary point of f of x. So if the Jacobian vanishes. Okay, so that's the extension that you probably saw in Math 115. And if you are one of my future students who have not seen Math 115, we're skipping essentially directly to the vector case. And when x is a scalar, then this is the ordinary derivative df by dx, and so that's the condition for a stationary point. And these stationary points can be local mins, maxes, or saddle points. Okay, so we're going to be trying to find stationary points that correspond to local minima. So, and why are they called stationary points? Here's the intuition. From the perspective of the linearization, so that's y of x equals f of x0 plus Jacobian function is literally a constant, so it's stationary. Okay, so at a stationary point, that puppy is 0. And so for the linearization, all we have left is this. And so as we move x, nothing is moving, the value of the function is stationary. Okay, that's where that comes from. Okay, so here I'm going to ask the question. If we are studying gradient descent, what is the gradient? Okay. All we have so far are Jacobians. Okay, so here it comes. Definition. For scalar valued functions, so it's important. The codomain is the reals. It's not R17, not even R2. So the gradient is, let me write down a bunch of partial derivatives. Whoops, there is no F2, there's only F. But there's an X2. This is by definition the gradient of f at x. All it is the Jacobian transposed. Okay? Remember the transpose? It takes rows and makes them into columns. Or it takes columns and makes them into rows. That's the transpose. Wow. All it is just a relabeled Jacobian, so how could that be important, okay? Why isn't it called Jacobian descent? Why is it gradient descent? So this symbol here is pronounced grad. Or gradient. If you're using LaTeX in Julia to make really fancy symbols, it's \nobla. I don't know where nobla comes from. I have no idea. So, you guys going to have any trouble computing a gradient? Probably not, because we did a pretty good job on the Jacobian, and the Jacobian was more complicated because it had multiple rows. Here we just have a scalar function. And the only thing is, the Jacobian, we put them in a row, and in the gradient, we put them in a column. Now, columns in Julia are the only true vectors. Everything else is row matrix, etc. So the big question now is, how does repackaging the Jacobian do anything for us? Well, how could it possibly be important? The answer is it leads to powerful geometric insight. And I will prove that. Okay. Just as a hint, this is thing to dot products. Aka, inner products. You with me so far? Okay, so we seek delta x such that f of xk plus delta x is less than f of xk where xk is our current iterate. So temporary solution, right? So we're just iterating towards our ultimate answer. choose delta x. So we go back to our linearization. F of xk plus delta x is approximately f of xk. Yes, it's the Jacobian times delta x. This came from xk plus delta x minus xk. Just plugging it in to the linearization. Okay, so that's the same thing as f of xk plus, this is going to freak you out, this is the gradient of f at xk transpose times delta x. Okay, before I write down the next things, look, vectors, they're like this, okay? Do you guys remember what you call the operation when on vectors when you take, well, let's do it for you. One of them, you transpose it, and then you multiply them. You get a scalar, right? So you just do that. Remember what that's called? The dot product, yes! Okay, that's why we said it's important, okay? So this is f of xk, and now the gradient shines on its own. I'm gonna make that as, try to make them nice. So that's, so just to make it super clear, it's the dot product of the gradient with delta x. We're trying to find delta x. We want this dot product to be negative or positive if we're trying to find a delta that makes f of xk plus delta x smaller. We need it to be negative, okay? We want that dot product to be negative. So, this is from Rob 101, so you don't need to write anything down. It'll be at the end of the notes. So here's two vectors in Rn. The inner product is just the sum of its V transpose times W. Okay, so that's what this is. It's V transpose times W. So I could also write this as, and that's not a dot, that's matrix. That's row vector times column vector. Okay? And there it is written out. So that's the dot product. It takes a row vector times a column vector, gives you a scalar, because that's how matrix multiplication works. The dot product is linear, linear on both sides here. So if I put a sum of V's and I dot it with W, it's just the weight times the dot product of V with W, and then the second weight, the second V with W. But it doesn't matter. I can put extra W's, and so it's linear on both sides. So that's just kind of the algebra of dot products. This is the important thing, okay? What does it mean for one vector to be orthogonal to another? Okay, so by the Pythagorean theorem, you can show V is orthogonal to W, or it's a right angle, if and only if the dot product is 0. That follows from the Pythagorean theorem. You can just write it down and prove it to yourself, okay? So right angles and dot products being 0 those are the same thing. Now, we'll see it in just a little bit. Suppose W, I'm not going to draw it, I'm just going to indicate it here. Suppose W was more like this. Then the dot product is positive. And if W were more like this, you can check the dot product is negative. We'll see that in a different context, okay? But 0 means right angle, positive means acute, and negative means obtuse. You remember those terms from high school geometry? Yeah, okay. Another little fact is, we don't need it a whole lot, but the norm squared of a vector is the dot product of the vector with itself. So that's the Euclidean norm, the sum of the squares, square root. Okay, so this is the key thing though. Right angles, there. Got that? That's the geometry that we're going to be exploiting. Went too far. Come on. Please come back. Okay, so V orthogonal to W if and only dot VW equals 0 if and only if right angle. That's geometry. And that geometry is harder to do with the Jacobian. So let me draw a picture. Do my best. Okay, so this is going to be the gradient. And this is minus the gradient. That's supposed to be a right angle, okay? It's close enough. These are all the directions orthogonal to the gradient. Now, orthogonal means the dot product is 0. What happens if we move in a direction that's orthogonal to the gradient? The function doesn't change. You see that? Dot product 0, this and this are equal. So all the points orthogonal to the gradient are unfruitful directions. So delta x orthogonal to gradient of f of xk implies f of xk plus delta x to first approximation according to the linearization. It hasn't changed. And those are unfruitful directions for minimizing Why are they unfruitful? Because we are literally spinning our wheels, okay? You move orthogonal to the gradient, you're not changing the function. You're spinning your wheels, okay? It's a constant. Now, in R2, where I've got this picture drawn, what is the dimension of the set of all directions that are orthogonal to the gradient? What's the dimension? Nobody wants to talk to me today. I'm being the mean professor, trying to get things out of my students, okay? Is a one-dimensional subspace orthogonal to the gradient, and that's assuming it's not equal to the zero vector. If the gradient were zero, then everything is orthogonal to it. Now, I didn't draw R3, but there is a two-dimensional subspace of directions orthogonal. So two-dimensional subspace that is unfruitful to explore. And so in Rn, there are n minus 1 directions that lead to f of xk plus delta x approximately equal to f of xk. So, if all of the orthogonal directions, are not bearing any fruit, they're not helping us change the value of the function, how many directions are left? Pi? E? 1. There's only one direction we can move. Okay? And so, if we move along this direction, we'll get the norm of the gradient squared, and we will increase the function. And if we move in the negative of the gradient, we'll get negative norm gradient squared, and that will decrease the function. So that's why it's called gradient descent. Okay? So hence, we have only one direction to move. Whoops. So we take delta x equals minus the gradient for descent and we take delta x equals the gradient for ascent. And so this gives us the gradient descent algorithm. Okay? xk plus, excuse me. Oops, I think I need to plug in. I've almost used up my battery, so let's do that. I suppose your laptops never get about to die at an inconvenient point in your lives, right? Never, ever happens to you. Okay, so the gradient descent algorithm is simply, you said delta x is minus the gradient, and then xk plus 1 equals xk plus s times delta x, and 0 less than s less than 1 is the step size. Okay? That's gradient descent. Okay, so once upon a time, you could get famous for making clever choices of this step size, but they've all been found now, so you can't get famous for that. At least it's unlikely that you can get famous for that. Okay, you understand where gradient descent comes from now? It's this picture, okay? You've only got, you can go up or down, and this formula where you do the dot product is what gives you the really nice geometric interpretation. Okay, so in your homework, you have a problem on volumes of revolution. Also called solids of revolution. Okay, let me give you a little bit of a hint. I mean, it's all in the book, but, you know, everything's in the book. So this is dealing with 3D space, so it's harder, at least for me. But this will give us a little bit of a break from what we were doing. X, Y, Z. In the XY plane, suppose we have two functions, and this is very similar to how when we were doing moments of inertia, etc. And it's bounded between A and B. This is now B, and here's X out here. So this is f of X, and this is g of X. And the assumptions are that 0 is less than or equal to g of x, less than or equal to f of x. So f and g are bounding some body in the plane. We have a point x. So this would be f of x. This would be g of x. And then we make a little bitty tiny rectangle here. And its width is dx. Okay, so solids of revolution, what they're asking is the following. If I take this body in the plane and now I rotate it about the x-axis, what does it form and what is its volume? Or I take this thing and I rotate it about the y-axis. Okay, and you can imagine you can get some really funky, bizarre shapes, okay? But this is a way to build 3D shapes, is you put the shape in the plane and then you rotate that. Okay, so let's do the x-axis. Let's take that rectangle, just the rectangle, rotate it about the x-axis. So the top point, it traces out this. What is it called? Circle. Yes. Okay. So I'm going to take this little tiny strip, and I'm going to project its rotation about the x-axis onto the YZ plane. Okay? Oh, go back. There we go. Okay, so let me do that one real quick. Actually, YZ plane is going to be going like this. Who's getting tired, my laptop or me? YZ plane. And yeah, I know, I gotta have the right tool selected. And it's not that one, it's this one. What the heck? Oh, I'm making a mess of it. But I'm gonna take that and try to draw a circle. Not a very good one. The radius of that circle, R2, is f of x. That's the top point here. Now, I rotate the bottom point and I get another circle. If g of x is 0, then this radius is 0, and I've got a circle. What is the area of the circle? Pi r squared. And r is f of x here, so it's pi f squared, okay? What is the area of the washer if r1 is non-zero? Okay? So at x, when I've traced this out about the x-axis, the area is pi times f squared of x minus g squared of x. You agree? Because it's r2 squared minus r1 squared. The differential volume is just a of x times d of x. Okay, I'll let you write that down. My drawing skills are horrible, and it's illustrated much more nicely in the textbook. But when I take and rotate this thing, yes, I've got this thing, it's called a washer, just like you have a bolt, a nut, and a washer. It's got a hole in it, it's called a washer, okay? If there's no hole in it, it's a disc, okay? Now it has a thickness. That's the volume, differential volume, dx, okay? So I've got this object bounded by f and g, and now I rotate it around the x-axis, and I want to know the volume. I've just given you the differential volume swept out by that rectangle. So the entire volume, x-axis, is the integral dv of x from a to b. And that's pi, integral a to b. You see, we've tricked a single variable integral into computing a volume for us, okay? That's pretty cool. It's actually wildly cool. And it's much better when you can, if you've got a mechanical engineering background and you can do these things, or you've got a mechanical engineering bent and you can picture these shapes. I'm a double E, so I'm pretty wimpy at that, okay? So that's a volume of revolution of this object when it's swept out around the x-axis. Now, what if I do the same thing about the y-axis? What do I get? Okay, so let me just see if I can do show and tell. Okay, so this is that little rectangle. I sweep it around the y-axis. This is the shape I get. I'm just taking a line, essentially, right? So it traces out a cylinder. Can you picture that? This little rectangle going around. What is the area of this cylinder? Well, it has a circumference. That's x. Okay? Excuse me, the radius. So the circumference is 2 pi times x. It has a height. That's f of x minus g of x. So the area swept out by this little rectangle around the y-axis is the area of the cylinder, 2 pi x times f minus g. And its differential volume, this thing has a thickness. I took this and swept it around, so it's really a shell is what it's called. So a cylinder has no thickness, and a shell has a little bitty thin thickness. If you took a piece of really thin aluminum and just wrapped it around, or a piece of cardboard. Well, this paper has thickness too, okay? So it's just really thin. Okay, so my ability to draw has ended, okay? So, but this creates a shell. So it's a cylinder with radius x around the y-axis, height f of x minus g of x, and thickness dx. So we get a of x is just 2 pi radius times height. Differential volume is area times differential thickness. So the entire volume on the y-axis is just the integral from A to B of the differential volume. So I wanted to do this because it's really important to remember integrals are how you sum things up. What's the volume when you wrap it around? I have no clue. But I can easily compute the volume swept out by that little tiny rectangle. And then I get a bunch of these washers on the x-axis all stacked up. Or around the y-axis, I have a whole bunch of these shells, and I just add all them up as x varies, and I get the total volume. Isn't that amazing? That's what calculus is really about. And so this is integral A to B, 2 pi x. And so you'll need that on your homework this week if you already done it and you got it? Oh, okay. Have you done it? Good, so it's going to help you. So at least I help somebody here. Okay, so that's our break. Can we keep stopping early? I don't know. I think we got to set up the problem. We won't solve it, but we'll just get it going. And we'll do it in two cases. And the first one is just a single equality constraint. So here's the idea. I want x star is argmin of f of x, just as we had before. But now we're going to impose that G equality is 0. F takes Rn to R, G equality takes Rn to R. Okay, so, example. minimize the sum of torque squared. In walking, subject to the speed equals v desired. Let's say that's 0.9 meters per second or something. Okay, so that's a much more meaningful optimization problem. We're not just minimizing the energy we use, but we're accomplishing a goal. Okay, and so G equality here would be that speed minus V desired is equal to 0. Okay, so that's how we impose the speed is V desired. So that would be an example of that. We could fix the step length. Okay. And so our objective when we come back next week, and next week we've only got 2 more periods before spring break, okay? So let's all give it up for that. Our objective is going to be how can we make F small while keeping G 0? So that's harder to do. But the geometry that we just went through with gradients and dot products will show us how to solve that problem. And once we figured this one out, you guys remember Graham Schmidt? Sort of. You take a set of vectors and how to make them simultaneously orthogonal one to the other. We'll remind about that. But that is the steroid version of the picture we had here with just one vector orthogonal to another. That's Graham Schmidt. And with that sneeze, I officially close today's lecture.